So what we have here is the dependent variable that looks like this. So it's the frequency of heavy drinking measured by the question, how often did you have 6 or more drinks at one occasion during the last 30 days? It's the same variable that Bengt talked about before. And we see that we have this huge pile here of zeros in this case. And what we have to kind of model this is some covariates. We have the gender, the ethnicity, early onset of regular drinking, family history of problem drinking, and high school dropout. So we have some covariates to try to figure out why it looks like it does. So we're going to do this in 2 ways now. And this is very, very similar to the negative binomial model and the negative binomial inflated model, right? In that case, we started with the Poisson model, which was the default. In this case, the default is just a normal, so we don't have to do that. I think everyone knows how to do a usual linear regression. So how do we start? By shifting some probability or doing the censored normal or the Tobit model, which is essentially shifting probability to the lowest point, to the cut point or the floor point. We do that by using the censored. Like I said, if the variable is not continuous normal, the dependent variable, the outcome variable is not continuous normal, we have to specify what it is. Before we say it was a count variable, now we say it's a censored variable. So we say censored equals HD, which is heavy drinking. And then a B within parentheses, and this B is now from below, censored from below. We can have censoring from above and below. So this is B for below. And that's everything we have to do. And then we just specify our regression like we would. And the second alternative is then to add the inflation equation. So add the mixture at 0. So just like with the negative binomial, it might not be enough to shift some probability to the lower point. We might also have to model the inflation to add a mixture at 0. So in this case, it makes sense, with the heavy drinking example. There might be people that never drink, and there might be people that usually drink sometimes, but they just did it 0 times for this month. And the way to do that is simply by adding an I, so censored from below with inflation. And again, when we add the inflation, then we have to add the corresponding model for that. So we have to model the probability of being in the never drinker class. So we do that just in the same way. So it's very, very similar. All right, so now we're going to look at the data 2 part. So this was 2 models, two ways to do it. We had the censor and the censor inflated. Now we're going to talk about the 2-part data command, which we use to create data for the 2-part model and the Heckman model that Bengt just talked about. So the data 2-part command is a convenient way to create this variable, because what we essentially do is that we create one binary and one continuous variable from this original continuous variable. And we do this with the following rules. So if the value of the original variable is missing, if you have a missing value on the outcome variable, then both the binary and the new continuous variable will be missing, because the binary variable is whether or not you're a drinker, if you have 0 or not, and the second one is how much did you drink. And if you have a missing value, then we don't know if you're a drinker or not, and we don't know how much you're drinking. However, if the original variable is greater than the cut point, and the cut point in this case is 0, we can specify the cut point, but in this case it makes sense to have it at 0, and that's where we have the floor effect. If it's greater than the cut point, then the new binary variable will be 1, you are a drinker, and the continuous variable will be the logarithm of the original value. So we will take the logarithm of your amount of drinking, so to speak, and that is to better fit the normal assumption of that. And that's essentially what we're trying to do, is make this part look more normal. So in this case, I don't know if it makes perfect sense to use the logarithm. We will use it. It's the default. And we will look at other examples where we override this default and have no transformation. But essentially, if the other part here, the cut-off part, so the positive part, if it looks like a normal variable, then that's fine. But that's what we want it to look like. We want it to look like a normal. And usually, we have this long tail that we want to pull in by using the logarithm. So if it's greater than the cut point, then the binary variable is 1, and your positive value is the logarithm of your original value, so the logarithm of the amount of drinking. And if the original variable is less than or equal to the cut point, so if it's 0 in this case, then the new binary variable will be 0. You're not above the threshold, and the continuous variable will just be a missing value. You don't have an observed value for the amount of drinking. So as Bengt said, we can analyze this data in two ways. This is how we create the two-part data. The two-part data we can analyze with a Heckman model or a selection model, or we can model it with a two-part model. And like Bengt said, the main difference is essentially what we assume about the correlation, or if we model the residual correlation explicit or not. So that's the main difference. But we're going to look at the data two-part command to start with, which is the same for both of these models. And what we do there is we state the data two-part colon for a command, and then we say names equal HD. So the variable that we want to create a binary and a continuous variable from has the name HD for heavy drinking. And then what we want to call the binary part. So we want to call the binary part U here. So U will be the variable that codes for if you have a value larger than 0 or not. And then the continuous part, we will call that part positive. So positive and U are names. And remember now that positive is the logarithm of the original value. So if you want to write that or scribble, like Bengt says, you can just scribble, this is the logarithm of the original value here, which you can override, and we will do that in another example. But then they differ a bit in the analysis command. I will get back to that. I think we'll start by looking at the model command. And of course now, since you have a binary outcome variable, one part is binary, you have to specify that this part is binary. Like I said, if you have a dependent variable that is not normal continuous, you have to specify what type of variable it is. If it's a count, if it's a censored, in this case, if it's a categorical. So you have to specify that categorical is, U is a categorical variable, and also mention these variables on the use variables list. But then we move on to the model command, and they have similar regression first. We have positive and U regressed on the covariates. Both have that. But then in the Heckman model, to get this explicit estimation of the correlation between those two, the covariance, we have to add a factor. So we put a factor indicated by U and positive. And the default in Mplus is to fix the loading of the first factor. So the loading of the binary outcome variable here will be fixed to 1. And the positive will be free. And the order there is not arbitrary. If you have one binary and one continuous, it's always better to fix the binary one. And then we fix the variance of this. So the only free parameter here will be the loading of the positive part, and that will correspond to then the covariance between these residuals. And the model for the two-part is the same, but we don't have to add this factor because, as Bengt said, this doesn't come into the likelihood, so we don't have to bother about it. But then in the analysis command of the Heckman model, there is some technical things. We use the probit link in both cases, but then we have the M-convergence option here. And this is because the likelihood is very flat in this case. So this just increases the precision in the numerical precision. So this is how close does the numerical derivative has to be to 0 for the algorithm to converge. And I just wanted to say, and we have the number of integration points here. And I just wanted to say that the defaults in Mplus are really good. So if you feel uncomfortable working with details like this, then you should just trust the defaults and have the same analysis as you have down here. You can just skip this, but this is an option for people that are more advanced users, and also if you want to see how these things affect something. If you want to do a simulation study, for example, you can shift these things. And there's a good paper on the number of integration points that I will refer to several times, because I think that we will not have time to go into and explain these details, but it's good to read up about it. Okay, so now we're going to look at and compare these models. And actually, we cannot compare all four because they're on different scales, right? Because the sample selection model and the two-part model, as we specify them now, use the log of y for the positive part, whereas these use the original y. So we cannot really compare these two. So we have to compare the censored normal versus the censored inflated first, and then the sample selection versus the two-part. We will look at one crude way to actually compare even all four of these models in a couple of slides. But for now, we can just compare these two. And we can see here that the censored inflated model have a lower BIC. So even though it has almost double the number of parameters, it has better fit because the BIC is smaller. And when it comes to the two-part versus the sample selection model, the two-part model is somewhat better. It has one parameter less, and it has better BIC here. I will talk a little bit more about these outputs. All right, so let's look at some outputs from this. Let's start with the censored normal model. We have 4 models now that we looked at. So let's start by looking at the output from the censored normal, the Tobit regression. And let's look at the effect of being Hispanic. So being Hispanic here has a negative effect. So you're drinking less on average if you're an Hispanic person, given that everything is the same. And it's a significant variable. But as we could see, the inflated model had a better fit, right? So if we look at the inflated model instead, we have the same kind of regression here, but then we also add the inflation regression equation here. And now we can see something else. We actually see that being Hispanic is not longer a significant covariate for the amount of drinking. So it's a negative effect, but it's not significant. So there's no effect. Whereas for the choice, if you can call it a choice, of being a never drinker or a drinker, it has a significant positive effect. So in this case, Hispanic individuals are less likely to be drinkers than the non-Hispanic individuals, or I guess white Caucasian is the baseline here. But if a Hispanic person is a drinker, then the fact that this person is Hispanic doesn't affect how much this individual drink on average. So again, we see the kind of the new information that we gain from having this inflation equation, the utility of that. All right, so like we saw here in the model fit measures, the Heckman and the 2-part model was very similar. And actually, the Heckman residual correlation is significant in the Heckman model. So it's difficult to choose between them. The BIC might suggest that we're going to go with the 2-part, but also the correlation was significant. So that might tell us to go in the Heckman direction. And of course, this should be a choice of substantive reasoning, right? We should think about what makes sense. If it is a missing value, like the Heckman model suggests, or if it is an absurd value, like the 2-part model suggests. And I really recommend the papers by Duan there, because I think they're really good explanations of how to think about these things. And if we want to compare then the censored inflated versus the 2-part, they have similar results. One thing that you will see if you look at this is that the signs are flipped for being at 0 or not. And that's reasonable because in the inflation model, we model the probability of being in the 0 class. But in the 2-part and the Heckman model, we model the probability of being larger than 0. So we should have flipped signs if the models agree. Like we said before, the log likelihood and the BIC is not really comparable. So what we can do if we really want to compare a 2-part model to a censored inflated model is to calculate the probability of some specific value for some specific group. So in this case, we can calculate the estimated probability of 0 heavy drinking and the mean of heavy drinking for a subset of males who have 0 values on the covariates Black, Hispanic, early onset of heavy drinking, family history of drinking, and high school dropout. We can compare that to the sample values for these. So the sample probability or the sample proportion of 0 drinking is 0.44, and the mean of heavy drinking is 1.538. And then we can look at what the 2 different models predict for this specific case. And we can see that the censored inflated model and the 2-part model have very similar probability estimates for being for being in the 0 class here. Now we flipped the sign, so I've corrected for that. But the mean differs here. So this might suggest that the censored inflated model fits the data a little bit better than the 2-part model. But of course, this is a very specific case. This is not an overall fit measure. This is a fit measure for just this kind of point in the parameter space. But you could, of course, add more and look at a lot of different combinations and different subsets if you think that it's important to compare between these 2 models. So this is one way to kind of evaluate the fit, even though they are on different scales. And just to round up, I'm going to look at this variable again. And as an assignment here, you could think about having an ordinal approach. So you could keep treating this as a 2-part model. You can think about it as being at 0 or not. But then you could think about modeling this part as an ordinal variable, which kind of Bengt hinted at in the beginning. It doesn't really look continuous. And actually, it makes sense as an ordinal variable because we know that they're order categories, right? There are combinations of how many times you have engaged in heavy drinking. And there's not too many of them. If you have a 2-part here, then there's only 1, 2, 3, 4, 5, 6 categories. So it kind of would make sense. So how would you do this? Well, you would specify that the positive part of the 2-part variable is an ordinal or a categorical variable. But then you would not like the logarithm transformation anymore, right? Because now we're going to view it as an ordinal variable, so you don't want to take the logarithm of the positive part. And here comes in then overriding this default of taking the logarithm of the positive part, which is easily done in the data 2-part command. You simply say transform equals none. And this would also apply then to if actually this part did look like a normal distribution to begin with, and you don't want to use the logarithm transformation. If it is already a normal distribution, then you don't have to bother. So this is how you do that. So you can try that out. And you can see now that we have a lot of combinations that we can try to work with these piles or inflations of zeros. And with that, I think we have reached the break.